By the way, I think, yeah, I mean, in general, you know, you guys did quite well in the assessment, so that's nice. Okay. All right, so, okay, so the first question was, what is true about the following matrices, okay? Identity, Hadamard, sigma x, sigma y. Some are permutation matrices and all are unitary matrices. None are permutation matrices and some are unitary matrices. Some are unitary matrices but not all. Huh? What is the right answer? A. Correct? Some are permutation matrices and all are unitary matrices. Agreed? Anybody having any questions about this? Okay? Good. So we move on to the next one. Okay. What is true about the following vectors? Select all correct answers. Okay. V1, V2, V3. All pairs are orthogonal. Is that correct? Huh? No. Sure. Which are not orthogonal? Huh? V1? Pair. Huh? V1, V2 is not orthogonal? V1, V3 is not orthogonal? Huh? Everybody is saying different. Which one is not orthogonal? V1, V2 is not orthogonal. What is the inner product? Huh? V1, V2, what is the inner product? Then what is it? V2, V3 is not orthogonal. What is the inner product? What is the inner product? V2, V3, what is the inner product? Huh? V2, V3, what is the inner product? You are saying right, not orthogonal. Then you tell what is the inner product? No. Huh? V2, V3, what is the inner product? 0. So that is also orthogonal. V1, V1 is not a pair. V1, pair meaning distinct pairs. V1, V1 is not a, right? When we say pair of shoes, should be different shoes, no? Correct? Yes? I mean, okay, to be very, very correct, I should have written distinct pairs, but that is given, no? So, this is correct, huh? A is correct, all pairs are orthogonal. B, some have L2 norm 1 but not all, correct? Yes? Some pairs are orthogonal but not all. Some pairs are orthogonal but not all. Is that correct? Not correct. Correct, because all pairs are orthogonal. So correct answer is A and B. Okay? You are given one of the following states. Describe how will you distinguish them with certainty. Psi 0, psi 1. Apply Hadamard transform and measure. Apply sigma y gate and measure. Apply unitary this and measure. What is the answer? Apply? Ha. C. Correct? Why? Apply this unitary on psi 0. What do you get? Huh? On psi 0, what is the column vector you get? Multiply this unitary with this vector psi 0. What is the column vector you get? Huh? What is the column vector? 1 0. Correct? Then apply this unitary on psi 1. What is the column vector you get? 0 1. So in one case you get 1 0, which means ket 0. In which case one case you get 0 1, which is ket 1. So you can apply this unitary and measure, and you will get distinct outputs. Clear? Any questions? Clear? Which of the following can be expressed as a tensor product of two 1-qubit states? Psi 0, psi 1. None, only psi 0, only psi 1, both psi 0, psi 1. Both psi 0, psi 1. Correct? Agreed? This one just 0 comes out 0 plus 1. Here 0 comes out 0 plus I1, 1 comes out 0 plus I1. So 0 plus 1, 0 plus I1. Agreed? So this is both. Any questions? Yes? What is the state obtained at the end of the circuit? B. Okay? You start with 1, ket 1, ket 1. You do control not, Hadamard, just do the operations systematic one by one. Oh, we should not have this, no? Correct. This was not there. This should have been not there because we were just asking the state. I think this is an older version we are looking at. Is it the older version? Yeah, this is the older version. Sorry. Oh no. No, this is older version. Sorry. 1 second. Can you call him? We're looking at the older version. Yeah. This is the older version. This is not the right version. Just give me a second. Okay, so meanwhile we get the newer version. Okay, let's start looking at quantum computing applications. Okay, so quantum computing applications, what is happening is that currently what we have, what we call is the so-called NISQ era. Okay, what is NISQ? NISQ means noisy intermediate scale quantum era, NISQ. Noisy intermediate scale quantum era, NISQ. What does that mean? Okay, what it means is that you see, currently we have several companies, right? IBM, Google, Rigetti, IonQ, Quantinuum, Huawei, Tencent, whatever, several companies, even publicly funded institutes. They are all trying to build quantum computers, correct? And what they have managed to build, different companies are making different claims, etc. But, bottom line is now we have few hundred qubits. In fact, IBM Qiskit itself, we saw that they were providing few 100 something qubits for free, right? So we do have few hundred qubits quantum computer, okay, with reasonably low noise levels. Error as claimed is like one in few hundred gates, let's say. In fact, recently there was this announcement of the Willow chip by Google. So what they claimed there was that for the first time they have been able to make the physical error go below what is known as the threshold. Okay, what is threshold? Threshold is it's coming here. Huh?
Send to the mail.
Send to the mail. You want to do this? Huh? I take it out then. Yeah, this is the right one. This is the right one. Download. Plus plus. Okay, okay. Okay, good. Yeah. Okay. So, five done, right? 5 is the right one here. Okay, sixth one. Go to sixth one. Yeah. We have this unitary U and we have this circuit 1 1 Hadamard control knot unitary measurement. The probability of obtaining 1 on measuring the first wire at the end of the above circuit is 1 by 2. You could obtain that? Okay. Yes? After doing this, when you did the U, it didn't change anything, right? But you realize, right, that U is not changing anything, correct? Because it is only the first wire. Agreed? Okay. Seventh question. This one, what is the answer? 0. Easy, right? Because 2 will be plus 1, 2 will be minus 1. Agreed? And then half with 2 signs. Okay. Problem of determining whether a given natural number is prime or not is in the complexity class P. True? I don't know. I don't know is the right answer or true is the right answer? True is the right answer. Because there is an algorithm, AKS algorithm. Remember? Agrawal, Kayal and Saxena we discussed. That is the algorithm, deterministic algorithm for primality testing, which makes primes in P. Title of the thing is primes in P, right? Title of the paper is primes in P, correct? So primes is in P. This one D, correct? You just check slowly, you will get it is D. Like for example, you see 0 here, correct? Then if you do 101, it is 0. 101, number of ones matching is 1, correct? So it is 1. 101, 0, like that you can do, correct? Okay, next one. Which one of the following is false? Tn is 7n cube minus 9n squared plus 10n plus 20. What is which one is false? D. Because A is true, right? It's order n cube, 7n cube. Omega n square, yes. If it's 7n cube, it is omega n square. Theta n cube, also correct. Correct? 7 times n cube. Small o of n cube, not correct. Small o of n cube is strictly slowly growing than n cube. It is not strictly slowly. Small omega n square, correct? Because strictly faster than n square. Correct? Yes? The Euclidean norm of the vector this is this vector is 4, correct? Yeah, you just verify that one. Do the calculation. It is true. Anybody having any doubt, please stop. The set of vectors, this one is a computational basis for 4-dimensional vector space. True or false? True. 1 0 0 1 0 0 1 computational basis. Correct? Very good. The function g defined as this satisfies Simon's promise. True? What is the string S for that, for Simon? Yeah, you can see 1 1 1 is here, 1 1 1 is here. So common is 0 0 1 0. Parity is bitwise parity of 0 0 1 0. Bitwise parity of 0 0 1 0 is 1 0. Bitwise parity of 0 0 1 0 is 1 0. Then common is 1 1 0 1 1 0. 0 1 1 1. What is the bitwise parity? Bitwise parity of 0 1 and 1 1? 1 0. Correct? Eh? So this satisfies the Simon's promise. Agreed? Grover's algorithm provides exponential advantage over classical randomized algorithm. True or false? Huh? Somebody saying true? No? True or false? False. Because it provides quadratic advantage, not exponential advantage. Correct? Okay. Next one. This one. Equal. So you could do it for every input. 0 0 0 1 1 0 1 1. Yes? See, it's easy to see one thing. I'll tell you what. If the input here wire is 0, correct? This gate will not get activated, right? Control not. Agreed? So Hadamard followed by Hadamard identity. So if top wire is 0, this whole input goes 0 0 0 0 0 1 0 1. Agreed? Here also 0 0 0 0 0 1 0 1, because this gate will not get activated. Now let's say 1 0 1 0. Hadamard will act as 0 plus 1. C0 will not do anything. You see, 1 0 0 plus 1 goes 0 plus 1. If you do not on that, because control not will happen, right? Because the top wire is 1. Control not will happen. That means not will happen. But 0 plus 1 goes to 1 plus 0. 1 plus 0 Hadamard back to 0. Correct? So 1 0 goes to 1 0. Now you will note that 1 1 goes to minus 1 1, because 0 minus 1 swap, 1 minus 0, that is minus. So 1 1 goes to minus 1 1. That's exactly what happens in this gate. Agreed? Control minus 1. Yes? Any questions? All good? Yes? Okay, now let's put that one. Okay, yes. So, as I was saying, that what is happening? See, what people are trying to do now is that if you have some noise per gate for quantum computers, you can only run it for some number of gates, some depth, correct? After that, the noise will just become too much. Agreed? So you have to do error correction. Okay? Error correction. So you have to implement error correcting codes. But what happens is, in order to implement error correcting codes, you need more ancilla bits, right, to run the code. More bits, more qubits, more gates, because they will be part of the encoding of the error correcting code, decoding of the error correcting code and all that. So apart from your core computation that you want to do, you have to do this additional computation also for error correction, correct? But now you have these additional qubits, additional gates, they come with their own errors, right? You implement that, but the point is even those will have errors, right? So there is this trade-off, okay? You are doing error correction, but due to that you are increasing your number of qubits, number of gates, which is causing further error to accumulate, etc. So you have to fight, okay? There is this trade-off. So what people have calculated is that if the physical error, that is error per gate, is below a certain threshold delta, then these error correcting codes win over that error, okay? If it is below a certain threshold delta, then the error correcting codes will win. If it is more than that, the error correcting codes will lose, correct? Because the error will accumulate very quickly. So that is the threshold delta, okay? Some threshold delta. Now Google claims that for the first time in the Willow chip, they have managed to go below that threshold. That means now they have the potential of actually going ahead and implementing the error correcting codes, okay? Now once you have error correcting codes, then you have the hope of building larger and larger scalable quantum computers, fault tolerant scalable quantum computers. The point is, in the classical computing, they don't use so much any kind of error correction. You know why? Because the hardware itself is so good, right? the chips, they have so many millions and billions of transistors, right, in very small space. But all those transistors are very, very good. Okay, they have very, very high fidelity. They don't fail. Okay, so therefore, they don't need much error correction, correct, for classical computing. However, quantum computing, you have to do error correction. Okay, you have to do error correction because each qubit, each gate will interact with the noise environment. See, what is the kind of the trade-off that we are having in a quantum computer? If you see, look, we have seen now that in order to run a quantum computer, any quantum circuit, we need to have these superposition over large number of qubits, right, and run it. In Shor, for example, you have to have superposition over so many qubits and run it. So we need to be able to maintain and do operations on a large number of qubits in superposition, correct. However, if you see, so we are looking at larger and larger systems we want to maintain in superposition, correct. But now you see, if you make it larger and larger system, so small systems, you know, one photon, one electron, one ion, few photons, few electrons, microscopic systems, correct. These are microscopic systems. Now you try to accumulate millions of electrons, billions of electrons, like that. You get larger and larger. We call them macroscopic systems, correct. Like for example, we are macroscopic objects, very big, made of so many atoms, so many molecules, electrons, protons, neutrons, whatnot, correct. So what we want is that macroscopic systems should not be in superposition, correct. Yes, if I am standing here, you should be able to see me standing here, not a superposition of here, here, here and here, agreed. If we are crossing the road, we should know where the car is coming from, correct, not a superposition of all positions on the road, in which case we will not know where to cross. So for the stability, even just our existence itself, we need that macroscopic systems are not in a superposition state, correct. So that is one end, okay. So that is the end at which nature operates. Macroscopic systems are not in superposition, and that is good for us because otherwise we will not even exist, agreed. So that is good for us. And why it is happening? Because our systems, any macroscopic system, is always in contact with the environment, correct. So it is always interacting with the environment. There are so many particles that are going through our body, so many neutrinos are passing through our body all the time. We are interacting with air, molecules, this, that. So much interaction is there. So therefore, that interaction decoheres the system. What is meant decoher? Means it goes ahead and measures the system in a sense. Think about it. Remember, what is our operation quantum circuit? We were doing this unitary evolution in superposition and then going ahead and measuring to get the classical outcome. Yes. So that is what it is. The environment measures the system with this interaction. Therefore, the system goes back to those classical states, is no longer in superposition. So in order to prevent the environment from interacting with the system, see, in a quantum computer, so you might have seen this kind of an image, right, of a Google quantum computer, correct. Most of it is basically a refrigerator, okay. Most of it is refrigerator. I think the chip is somewhere below, somewhere here, but the bulk of it is basically refrigeration. Why it's refrigeration? Because they want to isolate the system from the environment, okay. The temperature of the environment around the system should be very, very low. They try to bring it to below Kelvin, micro Kelvin, okay. Currently we have room temperature here. We make the temperature 20 degrees something, we start to feel cold, right? 20 degrees centigrade. How much Kelvin it is? Huh? 293. Correct. 290 Kelvin we feel cold. That one is what? Below 1 Kelvin. 0 Kelvin is the absolute zero temperature. 0 Kelvin is the absolute minimum temperature possible. Theoretically even 0 Kelvin. They make it below 1 Kelvin. 10 to the minus 3 Kelvin. Okay. Correct. That is the kind of isolation they provide to the system. Okay. But the thing is, okay, you can isolate the system, but then you have to also do gates on it. You cannot just leave it like that, no? So you have to do gates on it. So again you have to interact with the environment. Correct. You have to shine some lasers, this, that, something you have to do. So there is this trade-off. You don't want the system to leave the superposition. At the same time, it must interact with the environment to provide to go ahead and do the gates. So that is the trade-off. Not easy to implement. On the other hand, the other trade-off is also that nature itself doesn't want large superpositions. Okay. So that is you are fighting against nature at that end also. So basically, bottom line is it's not easy to implement such quantum computer hardware. That's the reason people have been making this effort for 30 years, and they have managed to reach 100 something qubits at this point, with some amount of low enough error per qubit per gate. So, right, the different companies having different kind of things. So now, that is what they call the NISQ era. What is the NISQ era? Because it is noisy, intermediate scale, 100 something qubits, quantum, correct? Noisy, intermediate, till we have error correction, till we don't have error correction implemented, it will be a NISQ era, correct? Noisy. So, you might have also heard of this company D-Wave, okay? D-Wave has what they call it as a quantum annealer. They claim 2000 something qubit quantum annealer. Quantum annealer is something specific, okay? It is more related to optimization, okay? Optimization. It is not like a gate-based computer. It is not like a universal computer, gate-based, but it is a specific thing tailored more for optimization. So basically, for example, so scalable fault tolerant quantum computing requires tens of thousands of qubits and millions of gates, for example, to run Schwartz algorithm. Okay, tens of thousands, because you have to implement error correction. Schwartz algorithm we cannot hope to implement without error correction. Okay, so you have to implement error correction. There will be a lot of peripheral qubits, lot of peripheral gates, tens of thousands, millions of gates. So that would need scalable quantum computers. Okay, that is highly unlikely in the NISQ era. Okay, where you have no error correction. So this is likely to take some time. Okay, so this is one thing. Now, what are the quantum computing applications that people are trying to explore? One is simulating quantum systems. What does that mean? We'll see. Optimization, machine learning, cryptography. Okay, different domains in which people are trying to look for quantum computing applications. All right, so there is this famous saying by Richard Feynman. I don't know, you guys might have heard of it. Nature isn't classical, damn it. And if you want to make a simulation of nature, you would better make it quantum mechanical, and by golly, it's a wonderful problem because it doesn't look so easy. Okay? So what he's saying is, if you want to simulate nature, because nature at microscopic scales exhibits quantum mechanical uh, operations, correct? Quantum mechanical nature, uh, uh, characteristics. So therefore, if you want to simulate that, you have to have a quantum computer, correct? Suppose we have some molecules, okay? So people are looking for applications like, in biochemistry, drug design and all that. What is happening? You have to simulate some molecules under certain control conditions, what they do, what is their behavior and all. But because these are small elements, microscopic elements, under those circumstances, they exhibit quantum mechanical behavior, okay? So you have to simulate those molecules, how their quantum mechanical evolution is taking place, correct? Now, if you want to just do it using classical computers, there is this exponential scaling. Remember, n qubit state, the unitary is 2 to the n by 2 to the n, correct? N qubit state, the unitary will be 2 to the n by 2 to the n. In order to simulate that, even 100 molecules, 2 to the 100 by 2 to the 100, cannot. Agreed? Yes? And I'm just saying 100 molecules, but each molecule will have so many atoms, so many electrons, this, that, right? So each of these physical systems will have that kind of scaling. So therefore, what we want to do is, in order to simulate the evolution of even few qubits, 100 qubit itself, we want to do it through a quantum computer, not via classical computer, correct? Classical computer, if we do, it goes out of proportion very quickly, correct? So I mean, just to get an idea of the scale, okay? If we say 2 to the 100, okay, just to get some sense of how large that number is. How much time has passed from the beginning of the universe? Huh? Okay, according to the Big Bang theory, okay? Some people may or may not believe in the Big Bang theory, but let's keep that apart. But assuming the Big Bang theory, how much time has passed from the Big Bang? Huh? Close to 14 billion years, 13.8 something, give or take, 14 billion. 14 billion, 1 billion is how much? Billion is 10 to the 9, correct? Agreed? Billion. Years. Year has how many? 365 days. Let's do 400, doesn't matter, give or take. Okay? 400 days. 1 day has how many hours? 24 hours. 1 hour is how many seconds? 3600 seconds, correct? Clock speed, usually, you take the best supercomputer, clock speed is usually 10 to the 9, correct? 10 to the 9 hertz, correct? I give you 10 to the 10. Even better, you want, I give you 10 to the 12, okay? So, 10 to the 12. This is the maximum number of operations that if we started a supercomputer at Big Bang, it would have done, correct? How many it is? Okay, 9, 12, 21, 23, 25. Another all this give or take. I make it 10 to the 30. ठीक है? Correct है? Give or take. Okay? 10 to the 30. We're talking about 10 to the, we're talking how much? 2 power 100, correct? Actually 2 power 100 is 10 to the 30, right? Because 2 to the power 3 is around 10. But I can easily make 2 to the power 200, for example, correct? Because I want to simulate, no. molecules. 200 atoms or 200 electrons is not a big deal, right? We want to do larger and larger, several hundred thousands of such qubits. Okay. For Shor's algorithm, we are saying we need several hundreds of thousands of qubits. So if you do this kind of scaling, not possible. We have to wait for another so many big bangs. Correct? Huh? So not possible. We have to get to quantum computers. Okay. Now, so that is the quantum simulation problem. Quantum computers can simulate quantum systems and processes efficiently, right? Now, these include what is known as the BQP hard problem. Okay, what is BQP? BQP is, see, I think Professor Subbareddy talked to you about what is P, right? Class of problems which can be solved in polynomial time using a classical computer. So class of problems that can be solved in polynomial time using a quantum computer is called BQP. Q for quantum, P for polynomial, B is for bounded error. Bounded error, quantum polynomial time. Why bounded error? Because quantum algorithms are inherently will have small error. Remember, each time there is a measurement, this, that, every time. Shor's algorithm also we saw, Grover's algorithm also. Always they will have some error. Hardly very few situations are where they are errorless. Correct? But generally they will have some error, but doesn't matter. The error can be made very tiny. Okay? Easily I can make the error 10 to the minus 6, 8, 9, whatever. Okay? Tiny error. So that tiny error doesn't matter. Okay? That's not a problem. That's why we call bounded error quantum polynomial time, BQP. Now the point is, if you can simulate quantum computers, quantum systems, that means you can actually run a quantum polynomial time computation. Agreed? Yes? If you can run quantum polynomial time computation, of course, you cannot do that without error correction. Correct? Because you have to do scale. When we say quantum polynomial time, we'll say, oh, you can run an n cube computation. But n cube computation for what? For n becoming larger and larger, right? N 100, 200, 1000, 10,000, you should be able to run that computation. Correct? That you cannot hope to do without error correction. Agreed? So therefore, we are talking about BQP. What is known as BQP hard? What is BQP hard? For any complexity class, a problem is called, for example, for NP, right? NP hard. A problem is called NP hard if every problem NP can be reduced to that problem in polynomial time. Correct? So similarly, BQP hard problems are problems where every problem in BQP can be reduced to those hard problems in polynomial time. Now, so we don't believe, again, this is a belief, we don't believe that BQP is inside P. This we don't know for sure. We don't believe that BQP is inside P. So if BQP is not inside P, if I have to do a simulation which can happen in BQP, I don't hope to do it in P. Correct? Especially if it is a BQP hard problem. If you can do it in P, then whole BQP will go inside P. Correct? But we don't believe that BQP is inside P. If you ask many people to say, do you believe that factoring can be done in polynomial time? Many people will say no. Correct? Factoring, we have seen, can be done in quantum polynomial time. That is in BQP. But they don't believe that it can be done in classical polynomial time. Even they don't believe in randomized algorithms. Polynomial time. That's called BPP. BPP is bounded error probabilistic polynomial time. BPP. So they don't even believe that factoring is in BPP. So that is the thing. Now, so as I said, many of the applications of this kind of simulation of quantum systems is in study of material sciences, right? How do materials evolve under various conditions? Study of chemical engineering, catalysts, how do chemicals evolve under different conditions? Study of biomedical, correct? Protein folding, dynamics, drugs, etc. Many questions in physics involve simulation of physical systems. So they have wide-ranging applications. If we can basically evolve quantum mechanical systems in a controlled manner, we will potentially get a lot of applications in different domains. Okay. So that is going to be one very good thing that will come out if we are able to get and make scalable quantum computers, because then we will be able to simulate quantum systems under controlled conditions. Okay. That is called as quantum simulation. Any questions? Hamiltonian simulation. We are calling it Hamiltonian simulation. What is a Hamiltonian? Hamiltonian is something, it's related to unitary, okay? So we have seen unitary evolution, right? So when a system evolves, right? When we say, okay, there is a unitary gate here, correct? This is the input, this is the output. This input evolves under this unitary, correct? So this unitary is actually associated with a Hamiltonian, okay? That is called another matrix H, and e to the IH t, t represents the time. So basically the system evolves under that Hamiltonian H for time t, and the result is this unitary u, e to the IH t. Okay? Get it? You see, H is a Hermitian matrix. H is a Hermitian matrix, which is the Hamiltonian. It is the Hermitian matrix. So Hermitian matrix have eigenvalues, real eigenvalues. Okay? So therefore e to the IH t, t is anyway real, non-negative, time parameter. So therefore, you know, the different, this matrix has the same basis, has the same eigenbasis as the eigenbasis of H. Okay? And eigenvalues become what? If theta is an eigenvalue of H, e to the I theta t is eigenvalue of u. And now e to the I theta t is of the form e to the I theta, correct? Which is basically a complex number of magnitude. Correct? So that's the reason why you get a unitary matrix. Okay? E to the IHT, e to the I, but the I is important, there. I is important, the complex number. Okay? So that is Hamiltonian. That is the Hamiltonian. When you evolve the system under that Hamiltonian H for time t, you get the unitary evolution u. If you do it under different t, larger t, smaller t, you will get a different unitary evolution u. U depends on t, correct? U will depend on t, and also of course an H. So that is what is called Hamiltonian. Hamiltonian. It is related to the unitary evolution that we want to do. Okay, but of course, as we said, that if you want to evolve a system, a Hamiltonian, for our desired length of time, we will need fault tolerance. Good. So that is unlikely to happen in the NISQ era. Unlikely to happen in the NISQ era because we need fault tolerance for that. Okay. Then there are other things like variation quantum eigensolvers. Okay. So then people are basically exploring, okay, we don't have error corrected quantum computer, fine. But what do we have now? We have a few hundred qubits. Let us say in some low enough error. Okay, one error per 1,000 or something like that. Okay. What can we do with that? So people came up with this model, this hybrid model. What is a hybrid model? What you do is you do quantum processing for some time. Okay, but you can do it only for limited depth, right? Because if you do want to do more depth, then noise will accumulate. So you do it for limited depth. Then you go ahead and measure. Before the environment measures, you measure. Correct? You measure. You get some outcome. Using that one, you run some classical optimizer and feed in the parameters back to the quantum circuit to optimize the quantum circuit. Then you run it again, that circuit, for a while, measure, use classical optimizer, feed back the parameters of quantum circuit, run it again, do this. Hybrid model of computing. So you are able to harness at least some quantum power, right? Because you are running it for at least for some time. So you are able to harness at least some quantum power. That is what people are trying to explore. Can we come up with something useful in this hybrid model? Correct? Something useful. So one is called as VQE, variational quantum eigensolvers. What they are trying to do is basically they are trying to determine the ground states and ground energy of Hamiltonians. Okay. There are interesting, physically very, very interesting Hamiltonians for which we want to determine what is the ground energy or ground state. What is ground energy? Ground energy means eigenvalue, lowest eigenvalue. That is called ground energy. Okay. Energy is essentially eigenvalues. And eigenstates are energy states. So they are trying to determine what should be the lowest possible eigenvalue of that Hamiltonian. What should be the corresponding eigenstate? Things like that, suppose you want to determine, because that is what you would need to do if you want to understand what is the optimal state in which a certain quantum mechanical system can be in. So, in order to determine that, they are saying, okay, can we run such a hybrid model to determine or approximate, let us say, ground energy of Hamiltonians. Now, for this model, it is not very easy to prove, right? Remember, for Grover we had a provable speed up. Sure, also we had a proof that it works in polynomial time. But coming up with proofs in this model is not so easy. Okay. So provable speedups are not so easy to exhibit. So there are unknown amount of speedups, but people are working with it, trying to see. Because even sometimes, you know, you can't prove things, but the heuristics also run very well. For example, SAT is an NP-hard problem, right? So it is hard in the worst case, but there are SAT solvers. People use SAT solvers all the time. So they work very well in real world, for real world instances. So even if for real world instances, if certain procedure works very well, it is also very good. It is welcome. We don't have to necessarily prove things about it. Okay. But as long as it is at least doing well in the real world, for real world instances, that is also very good. So people are trying to explore whether these models could at least be helpful in the real world instances. Forget like formally proving things about it. But even if they are helpful in real world instances, also good. Correct? Yes? Any questions?
Sir, how is this different from phase estimations?
Phase estimation is very different.
There also eigenvalue we are finding.
Correct. True. We are trying to find the eigenvalue for eigenstates. Agreed. But by the way, there it is only for unitary. Remember? We are trying to find the eigenvalue for a given unitary. Here we are trying to do it for Hamiltonians. For unitaries, the eigenvalues are of the form e to the I theta, correct? Which is a complex number, the phase matters there.
Yeah.
The magnitude is not important. For Hamiltonians, the eigenvalues are real numbers, so the magnitude is important. They don't have so much the phase issue. I mean, the only phase is plus minus 1. But other than that, it is the magnitude which is important. Okay? You can think of it this way. An example of a Hamiltonian ground, figuring out the ground energy. You know about the three-sat problem? Satisfiability? You know? Raise hands who know. Okay. In the satisfiability problem, what we have is, we have a formula. Okay? Let's say a 3 CNF formula. Okay? A formula consisting of various clauses. And you want to know, is there an assignment to the variables that can satisfy 90% of the clauses or all the clauses? What is the maximum number of clauses that can be satisfied by any assignment to the variables? Correct? These are the kind of questions you ask. That is optimization. That is what you are asking. What will be the highest number of clauses satisfied is the same as lowest ground energy. Map it like that. Highest number of clauses, if you have any constraint system, right? You have any constraint system, maybe all the constraints cannot be satisfied together, correct? But what is the maximum number of constraints I can satisfy together? Correct? Yes? Okay, for those of you who are not aware of what is a CNF, let me just say. Okay, suppose I have variables x1, so I say x1 and x5 and x7, okay, x9, sorry, or then and x13 or x15 or x22 and something else and, okay. So suppose I have such M, what they call clauses, okay. Each one is a clause. We are talking about Boolean variables, okay. This clause is satisfied if either x1 is 1 or x5 is 1 or x9 is 1, because this is or, correct. If any of the three is 1, this clause is satisfied. C1, let's call this C1. This is C2, C3, Cm, correct. Now, if I have either x13 is satisfied, x15, x22, this is satisfied. Now, I want to satisfy as many as possible. There are M clauses. The point is, if I do some assignment, some clauses may be satisfied, some may not be satisfied. Then I change the assignment, these may be satisfied, these may not be satisfied. Something will happen, correct. I want to come up with an assignment such that as many possible are satisfied, correct. Now look, there are 2 to the n, suppose there are n variables, there are 2 to the n possible assignments to the variables. So brute force, if I want to check every, it will take me forever, correct. So this is an NP hard optimization problem. This is called as a 3 CNF, okay. 3 CNF because there are 3 variables in each. CNF means there is a conjunctive normal form, doesn't matter what it is, but the point is, bottom line is we have a bunch of variables, n variables, we have a bunch of constraints on the variables, and we are asking how many such constraints I can satisfy. So it's a constraint system. It is not free. I cannot just freely do anything. I can give an assignment, but then that assignment will satisfy some constraint, not satisfy some constraint. And then my question is how many maximum I can satisfy in that system. So this problem is not easy to solve, but there are classical heuristic solvers, SAT solvers, which solve this problem very well for many real world instances. In the worst case, this problem is NP hard. So we don't expect a polynomial time algorithm for it. But there are polynomial time, in fact, very efficient algorithms which do very well in practice. Correct? So this is what you can call is a Hamiltonian system. It's a classical Hamiltonian system. Whenever you have a bunch of constraints, that forms for you a Hamiltonian system. Okay? Now in the quantum case, what happens is that these constraints become different. They start these constraints are now represented by what they call local Hamiltonian. Look, these constraints are local, right? They're only on 3 variables. Local, although there are n variables, the constraints are local. Correct? Constraints are local. That's why, and then the generalization, the non-classical or quantum or non-commutative generalization of such systems is what is known as local Hamiltonian systems. Okay? Local Hamiltonian systems. There what happens that these constraints become now matrices. They get represented by matrices, which we are calling the Hamiltonian, Hermitian matrices. But those matrices, their action, the non-trivial action is only on 3 qubits at a time. Okay? For example, they could be projectors. There is a thing called projector. Okay, I don't want to get too much into these formal definitions, but think of it as a non-commutative quantum generalization of such what they call CSPs, constraint satisfying problem. Constraint satisfying problem, CSP. This is a CSP, right? Bunch of constraints we have to satisfy. So such CSPs, their non-commutative or quantum generalizations are known as local Hamiltonian problems. Okay? Now local Hamiltonian problem, this kind of a problem is hard, it's NP hard, 3-side is NP hard, correct? So there are local Hamiltonian problems which are what the quantum generalization of NP called QMA, QMA hard. Okay? Local Hamiltonian problems which are QMA hard, which is the quantum generalization of the complexity class NP. Anyway, so the point was that and for those Hamiltonians, if you want to determine the ground energy, remember it is as such a QMA hard problem, correct? Because for those Hamiltonians which are QMA hard, determining the ground energy is the same as trying to determine how many constraints you can satisfy, correct? So that also becomes QMA hard problem. So we cannot hope to solve it even in BQP. Remember, we do not actually expect to solve NP hard problems in BQP. Even using quantum computers, we don't expect to solve NP hard problems. Factoring is not NP hard. Okay? Factoring is not NP hard. QMA hard is even harder than NP hard. So we don't expect to solve QMA hard problems also in BQP. Okay? Now, so as I said, this is the hybrid kind of a thing that they're trying to do. In the NISQ era. They're trying to explore possibilities of what we can do. Okay. Now let's get to optimization, as I had mentioned. Okay. Optimization problems are something that we come up in real world all the time. Okay. For example, we have this map of USA. So many cities are there. Okay. what is called as a traveling salesman problem, TSP. You have a bunch of cities, you want to find what is the shortest route in which you can cover all the cities. Suppose there is a postman, he has to go and deliver mail in all the cities. He wants to do it in the shortest route. How to find that? This is also a NP-hard problem. Financial portfolio optimization. So many times there is some financial portfolio, so many different financial sort of objects are there, stocks, their derivatives, futures, options, etc. This, that. You know, they have different constraints with each other. You have to optimize among all the constraints. Also, hard problem. Correct? So, in all of these things, you need to implement some or the other optimization. Also, for example, in many times logistics, right? There are these airplanes, they are taking various types of freights, then from this city to that city, how much weight, how much size, this, that, what is the best way to put the freight in which flight, at what time, etc. Okay? Bin packing, knapsack, these kind of problems. All are optimization problems, quite useful, of practical utility. But many of them are NP hard. So we don't know of efficient classical, we don't expect efficient classical or even quantum algorithms for them. So optimization heuristics, as I mentioned, often work in practice. A lot of optimization heuristics. So NP hardness, as I had mentioned, is about the worst case instances, not the average case or even real world instances. It's not about that. Real life has several instances which can be solved, which in fact SAT solvers solve it. So now again, for solving such optimization problems, people are trying to come up with hybrid approach. That is what is called as QAOA, quantum approximate optimization algorithm. Correct? Again, hybrid approach. You do a quantum processing for a while, measure some cost functions, optimize classically, then run classical optimizer and optimize your quantum circuit, run it for a while, measure, do it like that. QAOA. Correct? So there is also we are trying to approach the ground energy of a certain system. That system is a classical CSP system. But still the same objective. You are trying to approach a ground energy of a classical CSP system. In VQE, typically what you have is a quantum Hamiltonian system, where you are trying to approach a ground energy. Here it is a classical CSP system for which trying to approach ground energy. Okay? Any questions? Yes? D wave? No, D wave is what they call a quantum optimizer or quantum annealer. So it is not a gate based computer. It is not a gate based computer, but okay, it is sort of related to, if you might have heard of adiabatic quantum computing in a sense. What is adiabatic quantum computing? You see, what happens is, suppose you have a complicated Hamiltonian, a hard Hamiltonian, a hard constraint system like 3-SAT or something. Okay? You want to approach its ground energy or a ground state, right? In the 3-SAT case, a formula to the like assignment to the variables which can satisfy as many constraints as possible. So you have a hard Hamiltonian, you want to approach its ground energy, approximate its ground energy. That is, you want to your physical system to approach. So you start with H initial. Okay, it's easy. So to prepare the ground state of that is easy. See, we are doing a time evolution to this system, right? As such, there will be a h of t. and a psi of t, correct? Correct? We are doing a time evolution of the system. So you start with a easy Hamiltonian with easy to prepare ground state. You slowly change the Hamiltonian. Now adiabatic theorem tells us that if you do slow enough, if you are doing the changes in your Hamiltonian slowly, correct? HF is the hard Hamiltonian. So you have reached the ground state or close to the ground state of hard Hamiltonian. So that is very good. That is what is called as adiabatic computing. Okay, adiabatic means slow. Adiabatic means slow enough. Slow. Okay? Yes? Mike?
Like these are that approximate.
Exactly. That's the whole point now. You see? Unknown amount of speed up.
So we cannot give any performance bound also.
We cannot prove.
No,
But maybe you can do by testing actual.
but when we say approximate solutions, then they are the proof systems. Like else it become heuristic, na?
Correct. Heuristic. It's like SAT solvers. You see, SAT solvers you will not give formal guarantees. Oh, you know, for this I will give you this close. They will not give. But the point is, you just run it, and it runs in practice. It gives you good solutions for the kind of problems you encounter in the real world.
So it should be called quantum heuristic optimization.
True.
Because approximate means we have performed.
You're happy, correct? Right? So that's why I see unknown amount of seeders, so the runtime should be compared. That's why I see unknown amount of seeders, so the runtime should be compared to classical heuristic solvers. Because if you are going to do heuristics here, then you better compare to heuristic solvers there. Correct? You can't say I will do heuristics here, but I will compare to solvers there. Correct? You can't say I will do heuristics here, but I will compare to the worst case thing there. Then that's not apples to apples. If you're doing heuristics here, you also do heuristics there and classical heuristic solvers. Okay? And now there is also AI. Right? You know, the way AI functions, people don't really understand. Even the AI programmers don't understand fully well. Correct? It works. Then you don't know also how it works, but it gives you. Correct? Then you have to compare against that also then. If you have to exhibit quantum advantage, you have to say, oh, I am doing better than those AI solvers also. Correct? Yeah.
Not simulate by using quantum.
Yes.
Quantum. Then
Yes.
how we can go? How we can make use of the?
No, the thing is this. If you want to simulate using quantum computers or D-wave machine, for example, you can try to do that. I don't know how much D-wave is providing access to, how much free access is there or not, but IBM is anyway providing access to some 100 something qubits. So you can try to run it there, like for example using Qiskate and all that. You can try to run your simulators there. Not just simulator, you can even run it on actual quantum system, right? Gate based. But of course the limitation will be, it will be a few hundred qubits. The depth, the number of gates you can put is maybe depth, I don't know how much it can survive with reasonable noise, maybe depth 10, 15, 20, I don't know. But anyway, the point is it is going to be a limited system that you can simulate at this point. Although D-Wave seems to claim that they have several thousand qubits. But people are trying to do a lot of benchmarking on their systems, like, you know, okay, you claim you have several thousand qubits, okay, here is an optimization problem, can you solve it for us? They do that, but then they compare against classical solvers, and then they try to do a benchmarking, okay. So the D-Wave computer should outperform on that benchmarking, correct. So there people have written papers about it, you can have a look and see what is their conclusion about that benchmarking, whether they are convinced to what extent that D-Wave is outperforming classical computers or classical heuristic solvers. Yes, Mike.
Sir, in this, like the Hamiltonian solver, is it classical optimizer?
No. It is quantum, adiabatic quantum computing. This is adiabatic quantum computing.
Like you are, this is actually coming under QA
That
OA
benchmark.
only, right?
Correct. Huh? So there people have written papers about it. You can have a look and see what is their conclusion about that benchmarking. Whether they are convinced to what extent that D-Wave is outperforming classical computers. No, IBM, you are not even doing this. Yeah, IBM you'll have to do this way. That is,
Yeah.
you will have to first do a small circuit, then measure, then classical optimize and small. Like that you will have to do.
In
IBM.
okay.
And D-Wave also, they claim that they can do this, but it depends upon, again, they have also noise, they also don't have error correction. So how much they can do, to what extent they could do, how many qubits they can handle, all that is this one.
But yeah, it might be giving a better thing because it's closer to the system, right? Like if you want to do multiple crystal structure, I think this approach might be better. Yeah.
This approach, yeah. So that's what I'm saying. People try to do that. They try to see whether for their problems of interest, whether D-Wave computers are how much. Mike?
Problem which we have brought down to a nice Hamiltonian matrix form. Then we have three options. One is to go to QAOA, or where does adiabatic sit in between, sir?
Adiabatic this.
But it also has Hamiltonian.
Yeah, it has Hamiltonian. But the way it does it, the following. You start with you want to, basically, this is your Hamiltonian of interest, correct? You want to reach the ground state of that, or close to the ground state. You start with a simple Hamiltonian, with a simple, easy to prepare ground state. Then you do a evolution from here to here. Slowly, you are going changing. This is H0, this is H final. In between you have HT, but you slowly change it. When you're doing slow changes, adiabatic, okay. Now, but because this is a hybrid approach, it is possible in the NISQ era, correct? So again, people are trying to explore QAOA type algorithms in the NISQ era. Now machine learning, right? So machine learning, AI, of course, we all know these days. We use almost, so many people are using ChatGPT and all that. So of course, again, machine learning, things are hard to prove. Like provable speedups, etc. If you want to give a rigorous proof, it is not so easy. But again, they work very well in practice, right? So, and they have several applications: image processing, language, the large language models, right? LLM, language processing, recommendation systems, self-driving cars. So many applications are there for AI, ML, correct? Now people are also exploring these quantum machine algorithms, right, in the quantum regime. But again, because there are so many things are empirical there, right, we don't fully understand, we can't prove things. So we can't as such prove that they work better than classical, like provably. That is also hard to prove. But then we have to test them to see if they work well, correct? Examples are quantum neural networks, quantum tensor networks, etc. So again, we have to sort of design those models, run them, and see whether they are performing close to what we want to do. Now there is this thing called as quantum algorithm for linear systems. What is that? Suppose we have a linear system like this. You have a matrix A, you have a vector B. You want to solve for Ax equal to B. You want to find x such that Ax equal to B. Correct? Usually the linear system of equations. Matrix A, vector B. You want to find x such that Ax equal to B. Now these are used in a lot of places: recommendation systems, least squares, solving ODE, finance, etc. Linear system solving is useful at many places. Now we can solve them in polynomial time. Polynomial time in what? Polynomial time in the dimension, underlying dimension. Suppose there are n cross 1 vectors. A is an n cross n matrix. Then polynomial time in n. Then what happened? These people, Harrow, Hasidian, Lloyd, HHL, they came up with a quantum algorithm for solving linear systems. However, they claim that the running time is polylogarithmic in the dimension of vectors. Correct? So that in the regular classical case it is polynomial in the dimension. In this case they are claiming it is polylog in the dimension. See this? Huge amount of difference. Polynomial in n, let's say n is the dimension. It is polylog in n. Huge improvement, exponential improvement. However, there are few caveats. What is the caveat? The input comes b. Remember, in the classical case, b is a actual vector written down. A is a matrix that is written down. In the quantum case, b comes as a quantum vector, as a quantum state. Correct. B comes as a quantum state. That is, b, a vector b. Remember, if I have a 2 to the n dimensional vector, the corresponding quantum state will be n qubit. Correct. So that is how. If I have a 2 to the n dimensional vector b, I will encode it in the quantum state. What? The amplitudes of different bases will be coming from b. Correct. Okay, sure. Start, huh? Okay. Okay. So suppose I have such a vector b, okay, and suppose I have L2 norm of b is 1, okay. Then what we can do? We can write the state b, ket b. What is that? I from 0 to 2 to the n minus 1, b I ket I, correct? This state we can write like that, correct? Now this state is n qubit state, but I have encoded a 2 to the n dimensional vector in that state. That is how they encode b, this b. But if you start like that, then the output that you get is also encoded in that vector only, encoded in the vector. So then you have to measure to obtain the output also. You don't have all the entries of the output. Certain parameters of A, obtain each entry will not be easy also. That is another, this kind of an exponent. If you provide a quantum input in this form, if you measure, If you provide a quantum input in this form, if you measure, you get I with probability mod bi square. So that is called as a sampling access to the input. You are able to sample I with some probability. Now if you provide that sampling access also the classical input, then even classical algorithms are possible. Scala. So, but looking at this danger that this potential thing is there, the Schwartz algorithm can break cryptography, people are trying to come up with what is known, they call post-quantum cryptography. Honest parties are classical. Even the decoder is also classical, correct? Let's say banks. Currently they are using, it is not easy to make a guess on that. Development, standardization and development of post-quantum cryptography is critical for minimizing the chance of a security and privacy disaster, because then it doesn't require quantum hardware on their part, correct? It is like, still you have classical, like banks are there, they have current some crypto system, then they want to transition to something else, let's say lattice based or whatever, they can do that because that's all classical coding. It requires no quantum hardware on their part. So that is something they may find easier to do, cheaper to do than actually going ahead with quantum crypto systems. So this is what they are recommending. If they possible, people should try to do that. Research and development into practical commercial applications of noisy intermediate scale quantum computers is an issue of immediate urgency. That is what they are recommending. In the meanwhile, that we don't have scalable quantum computers, research and development into practical uses of what can be done in the NISQ era is of importance. Are there several engineering issues still left? Well, we can't say whether we will, I think nobody will want to venture there, okay? Because, venture there, okay? Because, as they say, there is many a slip between the cup and predicted that, we would amount of engineering, no? Right? This fabrication, this kind of thing. So it is not clear that you would be able to do it. That there will be phone pay, miniaturization of the students, correct? There will be no computer science students, correct? There will be no computer science, internet. So there was this project by NIST. They invited a lot of proposals for post-quantum cryptography, standardization. There were several submissions made. They have probably gone through and selected many of them, maybe finalized some of them, whatever. So their idea was, there is an urgency to protect information requiring long. Now quantum gate distribution. Quantum gate distribution, how much time we have? 5 minutes, wrap up? Okay. So quantum gate distribution, you might have heard, right? Quantum gate distributions is where I am trying to share some key. Suppose I have an n-bit key, I randomly generated my end, n-bit string. I want to send to Delhi, okay? Now what happens, if I am trying to send to Delhi, that time, if I am sending through a classical channel, fiber something, okay, then some adversary can tap onto it, can find out what the key is. No, one time, but if you want to do it without any assumptions, it is not possible. Zeros and ones, Eve can copy the zeros and ones and then let the thing go ahead, correct? Bob will not know any difference. Bob will not know, receiver will not know any difference, whether Eve has copied or not copied, correct? Intended to send this, but you got this, correct? That means some Eve is interfering. Then they will abort the protocol, correct? So if Alice and Bob find that there is too much interference, they will abort the protocol. If they find that interference is not much, then they will have proper keys shared between them. So that is the guarantee that QKD protocol. There were protocols, the first protocol was this Bennett and Brassard protocol 1984. Interestingly, this protocol was first presented in a conference where? In a conference? Eckert. He was our first director, Arthur Eckert, first director of Center for Quantum Technologies in Singapore. Okay. Later, several device independent protocols were proposed. What is device independent? You see, the problem is, okay, suppose there is some XYZ company, okay, they say, look, we make these nice QKD devices, okay, they go to a bank and they say, look, please use our devices to transfer your information from branch A to branch B, from Warangal to Delhi. Then login password, correct. Now those account login password, people have their lifelong saving or whatever, correct. So bank says, look, we cannot trust anything. Information is not getting leaked, okay. But the problem is the bank is classical entity. Suppose it's a small bank. It doesn't have any quantum lab or people working on quantum computing. Then it is just buying these devices from XYZ company. Then how does it trust it? That's a problem, correct? So they say, look, we cannot trust your devices. What doesn't matter what kind of certification you get, from where you get, whatever you get, we are not going to trust, okay? So that's a problem. So how to do that? So that is why what came was device independent cryptography. What does it mean? That means that you can take these quantum devices and you can check their functionality without doing any quantum operations. What you do is, they will give you some devices, you press some buttons on that, some lights will glow, red light, green light, whatever. So that means classical input and classical output. These are operations the bank can do. Press some button, get some red light, green light, note, and then check some predicates on classical input, classical output, perform some checks. If those checks go through, then that means that those quantum devices are working well. So classical test on quantum devices, that is device independent cryptography. You are not willing to trust the quantum states, you are not willing to trust the unitary operations, you are not willing to trust the measurements, you are not willing to trust anything about those devices, but still you want assurance on the functionality of the devices. How do you do that? You provide some classical input, get some classical output, and make some tests on that. If those tests go through, then you have confidence that that thing has gone through. So such device independent protocols were proposed for QKD, correct? Okay, but then there is another issue. The issue was that these device independent protocols only worked under the assumption that suppose some devices are shared between Warangal and Delhi. Alice is here, Bob is there. Alice gets some input X, she inserts the input. Bob gets some input Y, Bob inserts the input. Okay. Okay, let us say Alice and Bob, their devices are sharing some quantum state. Let us say EPR pair. Okay, one qubit here, one qubit there. Remember in our communication protocols they were sharing EPR pairs. Let's say some EPR pairs they are sharing and they have like this. Then this guy gets some input, makes some measurement, gets an output. Gets some input, makes some measurement, gets an output. Then they check some predicate. Okay, some predicate on combined predicate on X, Y, A, B. Okay. So if it goes through, if it is 1, okay. For example, the predicate like in some cases is like this. All these are bits. Okay. So predicate is X and Y equal to A parity B. Okay. This is called as the CHSH predicate. Okay. This was the first thing that was proposed by Bell actually, John Bell. Okay. Now, so therefore there is this game. Okay. You can play this game between Alice and Bob. If they're sharing quantum entangle between them, they're both getting input X and Y. These are all bits. Okay. okay? All are bits, and this is the CHS's predicate. Correct? They check if X and Y is equal to A parity B. Okay? Classical input, classical output, later they get together, they check. Is that happening or not? If this happens, okay. Now one can argue that if these devices are completely classical devices, no quantum entanglement, then this predicate will succeed with probability at most 0.75. Okay? At most 0.75. Probability over random inputs, random outputs. Okay? In quantum case, if they have quantum entanglement, they can win with probability. There is a precise number, but basically it is more than 0.85. So 0.85 probability they can still win in the quantum case. So what they do this test many times, and they see how many times they are winning. If out of 1000 times, if they win 0.85 times 1000, they are confident that this device has a EPR pair. Otherwise, if it's a classical device, it will only win probability 0.75. Correct? So that is the way they get confidence on quantum states and measurements. Huh? But now this has one issue. So this was actually the thing that was proposed by John Bell. Okay, this difference between 0.75 and 0.85, and then later experiments were performed. Actual quantum experiments were performed to confirm that. Okay, and a few years before there was a Nobel Prize awarded, right, to a few people, and that was precisely to conduct this experiment. Okay, they successfully conducted the experiment, and first time, because this is the time when, for the first time, very conclusive demonstration of quantum mechanical nature was given, right? Otherwise, there was all these, whether even for Einstein, it was not an easy thing to absorb, right? This famous quote of Einstein that God does not play dice or throw dice or something like that, right? So even for Einstein, he was thinking like, okay, quantum mechanical systems, we don't know the measurement outcomes because we don't know some other variables. Yeah? Once we know those variable values, then we will also determine the measurement outcomes. This intrinsic probabilistic nature of quantum was something that he was also not finding so easy to. Although Einstein was the one who had provided one of the initial evidences of quantum mechanics. When he proposed the photoelectric effect, correct? When he said that light is absorbed and emitted in quantas of energy. Absorption of light and emission is not continuous. It always happens in quantas of energy, which depends on the frequency of the light. That means he proposed those particles of light, photons, correct? For which he got the Nobel Prize, photoelectric effect. So that is one of the origins of quantum mechanics, quanta of light. Correct? But when the formalism finally came and this and that, he was still not so comfortable. Anyway, so that is what happened. And then when Bell's thing came, but this is later after Einstein, 60s. And then when the experimental demonstration was done, at that time it was like, demonstrated with much clarity the quantum mechanical nature. Because this difference between 0.7 and 0.85, you see, it's a lot difference. It's easily verifiable. And people started getting that 0.85, correct? So, anyway, so such things are done. Okay, I have to wrap up, I think. Okay, so such things were done. So this is what is kind of, you can imagine that something that leads to device independent cryptography. But there is another issue. The issue is that even quantum devices, what you need is an assurance that after these inputs are produced, they are not talking to each other. Because if they are talking to each other, then even classical devices can cheat. Correct? The input X can go here and easily you can find the answer. So what you want is that the classical devices are not talking to each other after the input is produced and before the output is produced. But how do you assure that? If these devices are provided by some XYZ company, they could be adversarial devices. They could be communicating with each other. So that is another issue. How do you assure that devices are not communicating with each other? So in fact, in the experiment, which got the Nobel Prize, they had to take care of this loophole, what they call as the no signaling loophole. That is, after the inputs are provided, They should not communicate. So what they did so much fast that they argued that light doesn't have time to reach from here to here before outputs are produced. You see? But they did it in a lab environment, maybe a few hundred meters apart or whatever, I don't know the precise thing. But then you have to do it so fast that light cannot go a few hundred meters. Correct? So that required a lot of precision. And they had to take care of a few other loopholes and whatnot. Okay? So what I'm saying is, but the point is you cannot, like day-to-day devices, you cannot rely on this thing. Oh, light doesn't have time to go from here to there. You cannot hope to build such precise devices because they'll be too costly otherwise. So the point is that people needed protocols which are leakage resilient. That is, even if these devices can leak some amount. So let us say they're trying to generate n-bit keys. We should allow them some leakage, maybe some delta times n, maybe n over 1000. At least allow some leakage. Don't say, oh, they cannot leak even 1 bit. Allow some leakage. So later leakage resilient protocols were also developed, okay, which said, okay, fine, even if we can assure that devices leak at most n over 1000 bits or qubits after the input is produced and before the output is produced, then also protocol is secure. Then also you can generate linear amount of keys. So those protocols were also proposed. And of course we cannot allow leakage of everything, right? If n bits are produced, then I cannot allow n leakage, because if n leakage is there, of course there is no guarantee. So I have to put some bound somewhere, right? So still now reasonable amount of bound people can produce delta n. So maybe if you put some bandwidth limitation on your Wi-Fi or this or that or whatever, right? You say, okay, look, I'm confident that my output will be produced within 1 microsecond or 1 nanosecond, and during this time I am sure that not more than 1 million or 100 million bits will leave my lab, okay, because my total Wi-Fi has this limitation, that limitation, bandwidth, whatever, something. So if you can give that kind of assurance, then also protocols become secure. Okay. Okay. Now QKD experiments have been done very elaborately already. Okay. Several Cambridge, Toshiba, Los Alamos, Geneva, various kinds of. You see, 1 Mbps. This is long time back. I'm telling you, 1 Mbps over 20 kilometers, 10 kbps over 100 kilometer. Over fiber, free space, ground to moving aircraft, satellite QKD, this Quest quantum experiments at space scale in China over several thousand kilometers have been done. This Mischius to ground, this is some satellite link, Mischius from China to Austria, again several thousand kilometers, and all that have been done. Okay. There are several companies working on QKD systems, ID Quantic, MagicQ, Quintessence Lab, several Japanese companies, Toshiba, other companies, Mitsubishi, NEC, NTT, etc. They have done some first world's bank transfer in QKD, using QKD in Vienna, used to transmit ballot results in Geneva, etc. So people have done few things with QKD. There are QKD networks now, several node networks in USA by DARPA, Europe, Swiss Quantum, Chinese networks, okay, QKD, in Tokyo, collaboration between NEC, Mitsubishi, NTT, Toshiba, etc. Future plans, several European, Asian quantum encrypted networks, up to 10 Mischius satellites, etc. So there are several plans. So QKD, there is movement that's happening. People are doing it at different levels. Okay, then there is a thing called quantum supremacy. Okay, that is also something that is related to the Google's announcement. They announced that they can do some task in 5 minutes which classical computers cannot do in 10 to the 25. They use the word septillion or something. Okay. What is that? Quantum supremacy is basically, okay, suppose we cannot even demonstrate a real world useful task. Doesn't matter. But as long as we can demonstrate any task, a practical demonstration of a quantum computation that is prohibitively hard for classical computers. There is no requirement to be useful. The task is any task. It need not be even a useful task. But what we want, we have to be able to do it in the NISQ era, and second, we have to have clear speed up over classical algorithms. So it is some task. For example, the task they used was random circuit sampling, correct? Which is just take a random quantum circuit and produce the output of that. Run a random quantum circuit, measure an output. Now, what is that? It could be junk, okay? It's a random quantum circuit. But they're saying it doesn't matter whether it's junk or not. Whatever output that is produced, we will argue that it is hard to simulate by classical computers. Correct? That's all. So, some tasks which quantum computers can do, but classical computers will find it hard to do. That is what is called as quantum supremacy or quantum advantage. Quantum supremacy, so to say. Quantum advantage, they say more in terms of real world useful tasks. Quantum supremacy is with respect to any task, doesn't matter what. So several candidates are there: boson sampling, IQP, RCS, etc. Good. So this NAS report we already talked about. So what is the bottom line summary? Summary is there are many quantum algorithms for many domains of application, correct? Simulating quantum systems, optimization, machine learning, cryptography. The algorithms that provably work are often not feasible with NISQ devices, correct? The algorithms that prove like Shor's algorithm, Grove's algorithm, they do not work on NISQ devices. They need scalable quantum computers, error correction. So therefore, now the major challenge is to develop useful algorithms for NISQ devices with provable speedups if possible. If not possible, at least demonstrable speedup for real world instances. Clear? So that is all I want to say about applications. Okay.
Thank you very much for making this course happen and making the course self-contained as much as possible. I think it was almost made it self-contained. So now I request the participant to have break for 5 minutes. Okay, no? After that, immediately we assemble for valedictory, quick valedictory. Okay, for certificate distribution and all. Okay, thank you. ఐదు. Now we formally start in a valedictory function of this GAN course. So now I request international faculty for this course, Professor Rahul Jain sir from Professor NUS Singapore and PI Center for Quantum Technologies at NUS Singapore, and head CSE Professor R. Padmavati madam. Actually, I was supposed to ask to come on to the dais and occupy their seats. Already they are on dais. Okay, so okay. Okay, thank you, sir. Thank you for occupying our seats and giving your time for valedictory. Thank you, madam. Thank you. In spite of some other alumni meet is also going on our department. Yeah, so madam has requested in the middle of that function. Actually, she was in that function. Okay. Now I would like to give overview of this course. Okay. So as you all know, 51 participants have registered for this course, but due to personal reasons, 5 members could not turn up for this course. So 46 if were actually physically present. And first of all, I would like to thank our director, Dean IRE and EAA, head CSE, and our international faculty, Professor Rahul Jain sir, for making this GAN course happen, and also the local coordinator of GAN, Professor from IIT Hyderabad, for sanctioning our program, okay, our course. Okay. And I also would like to thank the participants who are enthusiastic and young and enthusiastic, irrespective of their actual biological age, and they have been very active throughout the session, like, and they are almost with the frequency of our faculty, Professor Rahul Jain sir. Sir has not wasted even a single minute. Okay, if we had started 5 or 10 minutes late, sir has taken 20 minutes extra, so to compensate that. And today's session is an example. So we supposed to start at 10, but we started at 10:10, but it went up to 12:25, I guess. Okay. Okay. And as expected, we hope and out of all the participants, majority of the participants have given test, also attended almost all the sessions. Okay, maybe 1 or 2, some people have missed. Okay, and other 1 or 2 due to some other unexpected reasons, they could leave in between. Okay, and those who have taken test, majority almost except 1 or 2, all other people have participants have taken test, and they scored very well. Okay, no? So our average is, if you can say it for 100 marks, so then it is almost, we can say, more than 65. More than 65. So, yes. So we felt very happy while evaluating the answer scripts. So sir and myself, we both evaluated yesterday night, and we were happy the way. Only majority of the students, only 1 or 2 questions, common mistake. Okay, most of the students have done that mistake. And some participants, they were not able to write descriptive part. Only except for that, all other things were okay. Okay, yeah, okay. Now I request our head of the department, Professor R. Padmavati Madam, to say a few words. Okay.
Respected Director, Dean IRAE and International Faculty, Professor Rahul Jain, and the coordinators of this program, Professor Venkata Subba Reddy and USN Raju, and dear participants, good afternoon to all. Okay, so as per the Subba Reddy speech, I understood that you have performed well. 65 means all you got first class. Clap yourself for once again. It shows that you have attended all the sessions and listened carefully and wrote carefully the test. So that is the outcome now. That is the outcome. So already it is successful, but the certificate is to show others that you have done proof. That's all. Okay. So I mean to say certificate is nothing. You have learned already. You gained the knowledge already of this 10 days of stay. I feel that the stay at NIT Warangal also gave you more energy to listen the sessions, hope the other external factors. So thank you all. From various reasons you have you attended here, and some of the, I'm quite happy that few of our professors also attending this program. I thank you, sir, and once again I thank you all. Congratulating the coordinators for conducting and expecting more in future. Okay, thank you.
Thank you very much for motivating words, madam. Okay. So now I request our GAN course faculty, Professor Rahul Jain sir, to say some words about the conduction of course and any shortcomings from our side, or in general, whatever sir wants to say. Okay, yes, thank you, sir.
Yeah, so no, so I'm very happy. Firstly, thank to the coordinators, and it was a fantastic stay here at NIT Warangal. It's a very beautiful campus, very well maintained, very green, very nice, and thanks for the great hospitality. It was really nice. I think most parts of this course went smooth. I believe even for the participants, the stay and other logistics and so on. So I believe it was overall very well conducted thing, and I hope that the participants enjoyed. Yeah, there are at least a few things that they learned during the course, which they can take home, and maybe hopefully many of you are already teaching at your respective institutes. So in case you may want to conduct a quantum computing course yourself, right, at your institutes. So yeah, it was great, and I do not have any particular suggestions of improvement. I think most of it was fantastic. Maybe next time we can have maybe a little bigger board or something. And also I think the video capturing, although they tried their best, but sometimes capturing the video of the slides and the board, etc. Maybe there is something that can be done there. But otherwise, it was like fantastic. Okay, so yeah, all right. So great. Thank you very much.
So thank you very much, sir, for highlighting only positive points without telling any other thing. And I'll come to guest out and I'll ask you personally if there are any. Okay, thank you. Okay. So now I request, some one or two participants to quickly give your feedback. Yeah, though we have circulated forms and all, but formally, okay. Please pass on.
I had actually guessed that this opportunity would be there, so I have already prepared a few points. Thankfully, sir called. Thank you, sir. I'm just sharing a few thoughts. In case I am missing anything, which I would be definitely many things, I would love that my fellow participants can add coming here. Sometimes we feel genuine doubt. But once sir explains, we see that the question was maybe a little silly. But we will not make out that by the way sir responds to the question. Sir treats each question with so much respect and answers. So question might be small or big. So those who are listening will not even be able to make out. That is something we would love to build in our own selves, but we don't know how. We'll see. I'm talking about myself, but I think experience is similar to many of our friends here. That we got a lot of people who think alike. We got to know many people and got to learn from each other. We have approached different people and clarified our doubts, shared our thoughts and all. And the ever humble Venkat Subba Reddy sir, I think everybody unanimously agrees probability will be 100% for choosing the word humble when we are speaking about sir. And we got to know his sense of humor side when he was presenting such a beautiful thing, always with a smile and earnestness. And I would like to thank also Mr. Alfred, who took us through the memorable trip. Such a sweet person, coordinating everyone, because we would be lost in seeing the beautiful bridge and all, and he had to call us next time to watch the next beautiful thing. And one idea. The quantum algorithms start with problem where there is a promise, and then it moves into total problem where there is no promise as such, a very much real world problem. Similarly, we had a promise all these days that whatever doubts we get, we can immediately ask and get it clarified with Rahul sir, Professor Rahul sir, in person. After this course, we go out there in real world on our own, where there might be no such promise. There might be no such safety. We have to explore on our own, walk, fall, get up and walk again, and thus learn on our own. And I think this course has given us strength to make us feel that we can definitely do it. And when sir asks us to solve a problem, this one experience, uh, it was like trusting sir and jumping into water, coming to the board. And it's like rope. Generally, they teach in village like this only. They they tie a rope around our waist, and they'll push us into water. And we will be going inside thinking, but they'll have that rope in case we are too, in case situation is very dark, they'll pull up. So we understand that if we go something really lost or somewhere, sir will pull us up. So whenever sir calls is to go there and have that experience, that was beautiful. So all these things I in on top of my mind I wanted to share. And I think I'll start to feel loss of words for many other things. Everything has been great, smooth, and at the right time we got this course. Even in our college, we are introducing a course on quantum computing. So I feel like maybe I can prepare and teach that as well. So thank you everyone for making this happening. Thank you once again. Thank you fellow participants also.
If possible, one more, but make it as short as possible. Okay, okay. Thank you very much for the detailed feedback on the course. But most of the things, as usual, again. Okay, thank you. Okay, please come.
Yeah, so like, yeah, I mean, it was really nice that a lot of people, initially when I came, I was expecting more people locally, like from NIT Warangal or nearby areas. But then I find that there are a lot of people actually from, very, very far away places. So yeah, so it was great to see like an enthusiastic participation from the beginning, all the way. Okay, so great for that. Yeah.
Good afternoon to all of you, and good afternoon to our respective faculties and the whoever on the stage. But I would like to tell you one thing, that you are excellent. You are having excellent patience, sir. When you are dealing with us, even when I'm going with the faculty, I got an inspiration like that. Sir is having attaching a very friendly atmosphere. The coordinates providing friendly atmosphere over here, so that we will ask our queries easily, and every time we will interact easily. And sir is also interrupt the session and provide the solution to the extent that even why you are going that extent, sir, that this is enough, that's sometimes, but still you are prolonging to the extent that the participant will satisfy with their answer, so that only you will end up with that. So I am very, very inspired with your patience, sir. That is what I would like to say. And content is also covered most of the sessions, and I would like to explore more in the quantum computing. So I am very happy to over here because of the friendly atmosphere I get over here. Is I hope that I didn't get anywhere else in any workshop, sir, because Subbareddy sir is always, whatever the query it is related to our accommodation or anything else, sir is giving advices and giving suggestions, and whatever problem we get into, we immediately approach sir, and we immediately get the solutions from the sir. That is what I am like most. And and I didn't say any friendly. That explanation is very detailed. Every steps are gone through, but I didn't say in any workshop the explanation goes through every step. They just jump to the conclusion with the topic, conclusion, and some topics. But sir is going through each step, every step. Even sometimes in classes also, as a faculty also, we didn't go through that details also. But sir went through each step. That is the most inspiring thing. If I sometimes we didn't get a small steps also, sir went through that step and give some small example and covered every aspect, so that I will feel total inspiration, and I just feel like I would like to collaborate and explore all this environment and I met a lot of participants also. They are giving a very friendly atmosphere, so that I can able to come over here and talk in front of all of you. And I feel like they are also having a lot of positive enthusiasm, and they have a good opinions, views, perspectives that we will share and collaborate together in future also. I would like to come over here again and again. That is my final opinion throughout this session. I am very satisfied with this session. Thank you very much for this atmosphere.
So as we are almost running out of time, already ran out of time. Okay. Now okay. Thank you very much for the feedback, madam. Okay. It is motivating. Okay. And inspiring. Okay. Now I request Professor Rahul Jain sir to please present participation certificates to some of the participants. Okay. So first I would like to call upon Professor D.M. Vinod Kumar sir. So Professor Venkaya sir, Chintam Venkaya sir. Professor Venkat Lakshmi madam. Professor Anga Venkat Lakshmi. Okay, thank you sir. Dr. Sureka Samsani madam. Dr. Akash Yadav. Dr. Akash Yadav. Dr. Nitin Chatterjee. Mr. Nitin Chatterjee.
Hey, please, nobody should do this, huh? Nobody should do this, okay?
Mr. Karthikeyan, yes. Dr. Venugopal K. Mr. Payala Balakrishna. Mr. Nagaraju Battula. Mr. Nagaraju Battula. Mr. Rehan Kota. Miss Bonagiri Manoja Rani. Mr. Ratnavarshit Kolachala. Dr. Dr. Sumit Misra. Miss Miss Jonnalagadda Gayatri. Miss Panidapu Annapurna. Mr. Premchand Giduturi. Mr. Y. Pawan Manisankar.
Miss C.H. Varshini. Mr. Nanan Debak Chand. Mr. Sugam Kumar. Mr. Narahar Setti Vaibhav. Mr. Basuna Divya. Mr. Sai Sandeep Chintapalli. Mr. Manan Mujahid. Bhargav Mudoi. Bhargav Mudoi. Miss Vasigani Jansi Archana. Miss Chintala Chilaka. Miss Chilaka Shanti.
Sir, thank you very much for presenting the certificate, sir. Now I request our head of the department, Professor R. Padmavati Madam, to present certificates to participants.
Miss Renisha P.S. Miss M.K. Pushpanjali. M.K. Pushpanjali. Mr. Surasi Sharan Kumar. Mr. Ritvik Burra. Mr. Harish Kumar Pasureddy. Miss Polipalli Ruth Tejashwini. Mr. Shriyanshi Bole. Miss Revati Menon. Mr. Pashala Umesh Srichandra. Miss Banita Katwal. Mr. Aditya Ajit Menon, Ms. Janapareddy Vedavarshini, Ms. Josna Garikpati,
Thank you, madam.
అవును ఇంకా ఉంది. Yes. So all have performed very well, but we have, okay, no, we are going to distribute a chocolate to all the participants. And a bigger a chocolate which is bigger in size to top performing 5 or 6 participants, 5 participants, that's all. Okay, nothing much. Okay. So now I request Sumit Misra, RGI PT. Sumit Misra, RGI PT. So next, I request Professor Rahul Jain sir to announce the next top performing participant. Okay. This sir will give. Sir, please present.
Dr. Venu Gopal K. Ah. Okay. Yes. J. Gayatri. Very good.
Thank you, sir, for presenting.
Shit.
Vinkotuna. 5 top 5 on.
Thank you. Thank you, madam. Thank you. Okay. Sir. Okay. So thank you very much for okay. So thank you very much for making this event so to the what do we say? Uh, as per the guidelines and regulations given by GAN committee, okay, no, that IIT Hyderabad, we have followed attendance, everything as per their instructions, okay, and technically sir has taken care of everything, okay, no, non-technical coordination, two coordinators could manage from our side with the help of our administration, HOD, Dean, and Director, sir. And finally, I would like to thank all the participants who have spent at least minimum 12 days here at NIT Warangal and making this event a really physical event. Okay, no, it's not that some were first day, some were coming, next day some were not coming. It is not like that. I am very happy that all were there. Okay, no, whenever we circulated attendance sheet, usually in the afternoon session, sometimes we circulated, sometimes in the morning session. Irrespective of when it was circulated, all were present. We are very happy about your participation. And finally, we are running short of time. I would like to thank everyone who supported us directly and indirectly in making this course is partially successful. Thank you very much. Thank you. Thank you. Thank you.
Yeah, so thanks again to the coordinators for a fantastic.
And I hope sir also, Professor Rahul Jain sir, he said he enjoyed. I hope really he enjoyed some stay here to almost 12 days stay here, 13 days. Okay. So now I request all of you to please stand up for national anthem. Okay. Okay.
Okay, start.
We have to sing it, sings.
Jana Mana Adinayaka Jaya He
Bharata
पंजाब सिंधु गुजरात मराठा द्राविड उत्कल वंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मागे गाहे तव जय गादा जन गण मंगलदायक जय हे भारत भाग्य विदाता जय हे जय हे जय हे जय 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 हे.
All the participants to join us for lunch. Okay. At the same venue, Kalam Hall. And those who need fee receipt for registration fee, you may collect it from us, or we can send even soft copy also if you need that. So already we have.
So today the lunch is in ground floor, not in first floor.
Okay.
There.
So some in